Okay, what I'm going to do here is 2 quick modules on understanding yield and productivity, and try to relate this actually to some of the things that you more classically learned in ChE. And so yield is relatively easy to understand if you think about standard chemistry. So standard chemistry, this is really directly then related to stoichiometry. And so if you take a look at balancing, for instance, a growth equation, the result that you're going to get would be, for instance, for heterotrophic growth on oxygen, you'd have growth on sugar, 6. You're going to have a nitrogen source of some sort, so I'm just going to refer to this as NCI. That could be ammonia, that could be nitrate, whatever it is, it's going to be a nitrogen source of some sort. And then if it's aerobic, you're going to have a oxygen consumption term. And this is going to ultimately then go to biomass. Biomass has composition analysis of C, H, and O, X, Y, Z, which can vary. Inherent in writing it down like this, you've actually assumed a molar basis of 1. 1 as the molar basis for biomass. And so that's typical of what you do in a chemical reaction. And then what you'll have, the remainder of this will then be production of water. And so we'll have H2O. And then ultimately carbon dioxide as well, for example, epsilon CO2. And we're not worried about extracellular products or anything like that. It's just a generic growth equation here. And if you could fully balance this, what that would do is that would give you all of the definitions of yield that you need. For instance, one of the things that we'd normally like to know is how much biomass is actually made per amount of glucose fed, for example. So for instance, just taking 1 over alpha, for example, that would be equivalent to moles of biomass per mole of glucose, for example. And whereas a mole of biomass sounds strange, but if you have the chemical formula like this and you've assumed a stoichiometric coefficient of 1, it's pretty easy to calculate that. And so this is directly proportional then to grams dry weight per gram of glucose. So that's certainly one of the most common ones that we use as a yield, and it's very useful for estimating how much they're going to grow based on how much we feed them. For example, that number's about half to 0.6 for something optimal. So there are a lot of other things that you can do, but the problem is with this is that you can actually rarely close the mass balance entirely. So the problem here, is that you can rarely close the mass balance, close the overall. Stoichiometry. And there's a lot of reasons for that, one not the least of which is that you're making water and you're sitting in a pool. So this would be trying to keep track of the mass balance of babies peeing in the baby pool. So if you can't know how much water is being produced, clearly it makes it difficult to solve the number of equations and unknowns that you have here. That doesn't mean it isn't overall useful, and in fact you'll find that there's a tendency to use approximations, or at least elements like this. For instance, if we were to take a look at something like a respiration quotient, for example, the respiration quotient, respiration quotient is basically how much CO2 you give off relative to how much oxygen that you would take in. And so from a standpoint of just simply looking at this equation, that would be nothing more than epsilon over, I'm going to call that one gamma, I guess, since I'm not really good with the Greek system. So that would be here, epsilon, and that's, so this is the, if you will, the amount of CO2 that's given off, or the amount of, for instance, oxygen that's consumed, and clearly that on a molar basis would be epsilon over alpha. So in the photosynthetic world, there's also another number that you'll see used a lot, photosynthetic. Photosynthetic yield, ratio or yield. And it's sort of the inverse of this, and that's basically the amount of oxygen, O2 produced per CO2 fixed, or the inverse of that. See it both ways, I believe, actually. So, in a sense, this is a rigorous way. So this is what I would refer to as rigorous yield. And in many cases, for instance, for cases like photosynthetic ratio and quotient, we just measure those directly. We don't actually do the rest of the mass stoichiometry. We just simply measure, for instance, with a mass spec, this one, and then we use those numbers to be an indication of what's going on biologically in the system. So in a sense, then, that's in many ways it's not very predictive, and in many cases it's not very practical to actually have that information. That leads then to what I refer to next as sort of a practical yield. And a practical yield is what introduces a lot of ambiguity, I think, for some people, so we'll call it a practical yield. The emphasis is on measuring something that is useful, relative to something that's relatively easy to measure. And these in some way are going to be then related into ultimately what you're after, of course, in a practical sense here is the, like for instance, the amount of money for the product over the money for the substrate. And it's, obviously this is the kind of thing that you're concerned about, or at least headed in that direction. Looking at this in terms of what is easy and useful to measure. For instance, if I wanted something that would be analogous to the yield that I had over here, where this would be, for instance, a yield X on S, for instance, that would be yield of cells on substrate. The cells might be measured by optical density, so I would make a delta OD in optical density. And then substrate might be measured by, for instance, in terms of a change in, for instance, refractive index. So we'll call it RI. So refractive index is just an easy way to measure sugar concentration, and OD, or in a spectrophotometer, would just be a measure of how dense the actual cells are. And if you want to think of this in mathematical terms, you can say that, well, this is somehow equal to, say, K1 times grams dry weight. In other words, there's a relationship between those two. Refractive index is going to be, well, somehow measured related to the grams of glucose again, or grams of sugar. And everyone knows you have two things you don't know, or even if you do know them, you can certainly express that as K3 times the yield that we had over there, so grams dry weight over the grams of, in this case, glucose. So it's just another way to get to essentially the same kind of thing through easy measurements. And what you'll see, though, is that often in papers they make Okay. So the key aspect to this is that we're measuring something that is relatively easy to measure, and then that will give us this. So we're not really thinking stoichiometry anymore. We're simply trying to estimate, you know, how many cells are in there, how much is my sugar is actually being consumed. And there's a lot of other things that you can do. Anything that you could measure, for instance, proportional to the number of cells. Cells, for example, that could be proportional to, for instance, CFU, colony forming unit, CFU. Okay. What a colony forming unit is that it's a petri dish, and it's put a certain amount of volume on there, and you count the number of colonies. Okay, that's it. So CFU is proportional to cells if you have a flow cytometer, cytometry, things like that. And any measure that you can come up with that's proportional to the number of cells in there would be good. In the case of anything that's related to like media components could be proportional, for instance, to conductivity. Conductivity would be ions, you know, for something that's actually eating the inorganics in the system. So any one of those can be measured, and it just becomes a useful way to actually do it. Here, again, there's a certain aspect that I would say it's a problem. And the problem here, besides the fact that you have to make a correlation, so besides the correlations, i.e. Getting information like optical density as a function of grams dry weight, and getting those which may or may not be accurate. Okay. Question mark. Okay. You're working then with something where you are clearly looking then at how much has been consumed. Okay. And so this delta S, okay, is maybe not equal to the dollars, if you will, for the substrate. Because they're not necessarily eating it all. And so that type of a yield isn't the kind of thing that's proportional to this. It's more like a biological yield. How many cells, you know, because if they only eat half of the substrate, and then you're not penalizing them for not eating the rest of it, the actual amount grown is more like a what I decided to eat kind of thing, as opposed to what I paid for, and then you didn't bother to actually sort of eat it at all. If you take a look, then this gets to closer then to what you refer to as a metabolic yield. And so I'm going to go back to here. I'm going to erase this. And introduce yet another definition, if you will, of a type of yield, and that would be metabolic yield. And what we're really then talking about here is related to pathways, if you will. A classic one for this, for instance, would be like grams of ethanol. Per gram produced per gram of glucose consumed. And often then you can look at this then in terms of, you know, the actual pathways where you may have glucose and you're going down through glycolysis, down to pyruvate, and various ways you can get over from there. Acetyl-CoA, and you eventually go to ethanol. And so a metabolic yield is really sort of looking much more than at how much did I eat and how much did I make relative to that. And clearly you can start to see then here where it's not that far away from an idea of theoretical yield. In other words, it may be possible, depending on the steps that you're using here, that you would actually get to that. And so if you take a look then, this is really then much more about the efficiency, if you will, of metabolism. So as a biologist, this is the kind of thing that you definitely would be interested in. There are different organisms that have different pathways to ethanol from glucose, and the efficiency of getting there will determine which makes, if you will, more evolution sense. And from a practical standpoint, it also makes sense as well, because what you're really looking at is, basically these little, delta G of each of the steps that you're going through. And you may have a phosphorylation, something that knocks it up to a higher one, and then ultimately the net result of this gives rise to essentially what you will see in a given organism. Clearly now we're starting to talk about energy, and so that's another term that I'll throw in here, and that's the energetic yield. And or I already mentioned the other one, which is a theoretical yield. And one can start to see how this starts to get quite confusing. Like, for instance, one could look at it and say, well, if the theoretical yield is this much, delta G, going from glucose to ethanol, you could start to do things, say, well, let's say that it's 75% of theoretical yield. And then as a result of this, what you're saying is you're not going to penalize them for what they couldn't capture metabolically, and you're going to ask yourself, what is the measure of inefficiency that's in there? They're wasting 25% of the energy that they might have been able to catch if they did this according to theoretical yield. And so I think that this, one of the big motivators for this, it should be kind of obvious that ultimately the driver for energetic yields is when you're really talking about biofuels. And so from biofuel standpoint, of course, you're really kind of worried about, for instance, the BTUs in the ethanol that I made relative to the BTUs in the glucose, because glucose will burn that I fed. Okay, and you can kind of see that this kind of thing allows us now to really think along the lines of energetics and so forth, and alternatives, because if I take that same glucose and I make something else like butanol, okay, and then I can compare them one-to-one based on how much energy I managed to recover by doing those interconversions. So although yield is a simple concept, at least the way we historically look at it in stoichiometry, you can very quickly then see that it becomes confusing. So here we call it not a problem so much, but it's something you need to be aware of, is that there's what I've called niche yields. Okay? Different areas of research have a tendency to use certain conventions. In fact, they use them so much, sometimes they don't document them very well, and it becomes kind of confusing if you're looking across at a bioenergetics paper relative to a practical one where you just simply like to know how many cells would actually be produced and so forth. And so remember very clearly here that the problem that is that all the units may be the same. You may see grams of ethanol per gram of something else and so forth. And so you have to be very careful about being clear about what it is. So a gram of glucose not fed,
20 seconds.
but the amount that is actually consumed, those are very different terms from an energy standpoint. Okay, so the next thing that I wanted to cover here was productivity. Productivity is important, and other words that you'll tend to see will be tighter. the English version of it. And things like specific productivity, instantaneous, so on and so forth. There's a lot of words that I'm going to sort of be out here that are slight variations on this that we should be aware of. With the primary thing here is that this is a rate. Okay, and so we're looking at how fast stuff is being made. Okay, in the simplest terms, sort of the ones that you'll see most commonly expressed will probably be a volumetric productivity. And volumetric productivity represents the amount of product, if you will, per volume, per time. And so it's directly related then to a concentration or a titer. Or a concentration, however you like to look at it. Okay. It does not take into account how many cells are present in the reactor. Okay. In contrast, then, specific productivity is all about how many cells are present. And so here what we're really talking about then is the amount of product per gram dry weight per time. And so I'm not penalized by having a lot or a little cells in the reactor. All I'm normalizing by is how much work is being done by the individual cell. And so the way to be thinking about this is essentially, this is all about the cell effort, if you will. And this one here is all about utilization of your reactor. Simplistically, you can think that engineers tend to think a lot more about volumetric productivity because they paid for the reactor, and biologists think about it much more in terms of how each individual cell is doing the actual biochemistry. Okay. Now, if you take a look at it from that standpoint, just to put a notation in here, if we're doing assessments here, this one here would be reactor performance. And this one here will be biology performance. Obviously, a better performing biology with more cells in it will ultimately give you the better performance in the reactor, and ultimately that's the goal that you're going after. Now, in terms of how you evaluate this, well, most of the time what you'll often see is like a time course where you'll have something like the concentration of the product, which will be, for instance, product per volume, if you will, and it'll be a time course. Because you just simply take time points as you're growing your cells and making something like that, and you'll get data points. And the point is that if you just simply look at this in a pure mathematical sense, clearly, if I wanted to know something with this units on it, I could get that in more than one way. One of the ways that I could do that is to just simply have the derivative, right? Okay. And so this one right here would be the derivative dt of PV, and that has the right units of grams dry weight, grams per volume per time. It would be referred to here as essentially the instantaneous productivity. And clearly, instantaneous productivity is getting better and better, and instantaneous productivity is going to get worse once it tips over the top. In contrast, if I was looking at this from a standpoint of average productivity, what I would be doing at that same point is I would look at this. I would look from here, and this would be the delta t from t equals to 0. And then I would look at the productivity per volume at this point here, and that would ultimately then give me a delta PV, if you will, P for product per concentration, over a delta time, which in this case is just simply time, okay? And this would then be equivalent then to a average productivity. And you can see that there's a very big difference between these two, because the instantaneous productivity is going to start nearly zero, and then it's going to get high, and then it's going to go negative, okay? Whereas the average productivity is not going to ever go negative, because there's stuff in there, right? Okay, it's going to decline with it's going to slow down, if you will, but the average productivity here is not negative. It's, you know, some was made over that period of time. So you can see that in many ways, this is kind of the decision point, if you will, of like when to kill the run, if you will. Instantaneous productivity is telling you that, hey, you're not making money anymore relative to this point in time. So this may be like a kill the run question, okay? And this one here is more like the, how much did I make? What's happening is I'm slowing down how much I'm actually had made, but I still managed to make money, okay? It's just that at this moment I'm losing a little bit of money, but on average I made money over that period of time. And so those are the basic things that you can kind of look at that are here. Where this can start to get difficult, of course, is if I want to then convert between these things. And it's not unusual in a paper where they'll give, well, if they gave concentration of product with time, they might also give, well, something like optical density with time. And so this will be the growth curve, if you will. Okay. And so what you may see is that if I'm going to go about trying to get to this data, that is specific productivity, using this information down here, I'm going to have to take and digitize the data from both of these two, and then I'm going to have to do calculations in a spreadsheet. That's the only way I'm going to get at it. And remember that optical density is proportional to, well, it's proportional to grams dry weight per liter. Okay, so it's a cell concentration. So it's a product concentration, it's a cell concentration. Sometimes they might actually do total product. It won't be per volume. And so you have to be very careful about how these things come about and how you're going to actually then ultimately do the calculations, because you might take and make another plot. That plot might be productivity per volume, if you will, per OD, okay? And by doing that, what I've effectively done is that's equivalent to P over V, and OD is proportional to K1 times, if you will, grams dry weight per volume, and the volumes class out, and then you can see that you've now created something which is the equivalent of the product per gram dry weight, and then that plot, whatever it happens to be doing, and this is time here, and I make this on the y-axis. Now any slope that I get from this curve will then be the specific productivity. And remember then, the specific productivity doesn't have a constraint of always going up, because your cells can be kind of chugging along and they can make nothing, 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 nothing. In fact, if you take a look at something like a growth associated, there's a series of three things that I want to just cover here quick. How much time is left?
I got 40 seconds.
40 seconds. Okay, so what I'm going to do then is I'm going to talk about three types of additional definitions you'll see in productivity that are dependent on whether it's intracellular or extracellular. Okay. The other one is whether it's growth associated or growth dissociated, it may make it. And the third one is whether it's constitutive or induced, where you actually induce it. So we'll do that next. Okay, so to go into some clarifications about dealing with productivity, there are certain things that are introduced that make it a little more complicated. The first one I wanted to mention is intracellular versus extracellular. If you take a product, and if that product, for instance, is intracellular, then in a sense your productivity of your system is directly related to your dry weight. In other words, here your grams dry weight, okay, your cells are a product, okay? Because you're going to have to kill the cells to get the product out of it. And so your focus there in that sense is very coupled with, if you will, the grams dry weight. In contrast, if you take a look at something where you would have an extracellular product, okay, in this case there's no coupling at all to that. And so here what you have is a situation where essentially your cells are a catalyst, right? You don't have to kill your cells to get the actual product. So it might make sense to be trying to not have growth. So here you want, here you like growth. And over here, you don't want to have growth. And so, I'm sorry, here you don't want growth, I'm sorry. Okay, let me do that. If your cells are inside, if your product's inside the cells, then you really need to grow them. Okay, that's important. Over here, if it's outside, you could be making a lot of product because you have your reactor full of that. You're running your media through. And if your product's outside, you don't need to have growth at all. Okay, and yet now you have to relate how much you're making to how many cells are in there. So you can see the specific productivity is based on accumulation and of your product somewhere other than in the actual cells itself. Okay, volumetric productivity now is potentially the volume of the reactor. It may be the volume of the liquid that is passed through the reactor. Okay, and so you have to be very careful about how you define things, because when you say product per unit volume, okay, the units are the same whether you decide that to be the volume of the reactor system, or you may run 10 volumes of liquid through there. Now obviously your volumetric productivity expressed on a media basis is entirely different from the situation where they are not. Okay, and so the basis of how things are going, particularly with the extracellular one here, is that it allows for a very different way of expressing data. I call them, for instance, cumulative plots. And I'll be using that as an example for the homework that I had, where you can be looking at, how much is accumulating with time. And in theory, okay, if you have an extracellular product, there is no limit, right? You can continue to have a productivity where the grams of product is greater than the grams of the cells. Obviously, you can't have that in the case for the products inside the cells. In fact, if you think about it, if I have a lot of that, like for instance, oil production in algae, they say, oh, well, 50% oil. Well, then what now you have to worry about is that half the cells are oil, and half the cells are, well, cells. Okay? And so sometimes you'll see that people will try to subtract the biomass on an oil-free basis, because obviously these are the ones doing the work. They're the ones actually doing the biosynthesis. The oil can't make more oil. And so you have to be, again, really careful about how you make expressions if you're trying to actually keep track of that. The other thing is that this particular thing, when the product is inside the cells, then that's not like a titer where we were talking about concentration, but here we're talking about a content. This is where you say percent of dry weight. Okay, so lipid content is 30% of dry weight and so forth like that. So content becomes a very, very important thing when we talk about intracellular products, and concentrations or titers become important in the other case. The other one that I just wanted to quickly go over was the idea of growth associated and growth dissociated. Okay, so that's growth associated and so-called dissociated. And this is a very simple concept, and that is if it's growth associated, what you'll see is that as the cells go up, okay, then you have the product goes up right alongside it. And what you'll often see is something like this constant. So it may be 30% here, and it'll be 30% there. Okay, the same content is associated with that. In contrast, if I look at a growth-dissociated product, the cells will tend to grow. And then it's not unusual then what will happen after that is that the product may not even start to form until after they stop growing. Okay, so a growth-dissociated culture like antibiotics, penicillin, stuff like that, okay, once they stop growing is when they start to accumulate the product. Okay, and so you can imagine that your volumetric productivities and your instantaneous productivities, of course, are 0 for the entire growth curve. Okay, the specific productivity is horrible. Okay, they're 0. Okay, once you actually stop them from growing, now what's happening is you have them take off and actually make product. So that's growth associated. The last one that I wanted to mention here is constitutive versus induced. So that's the third one. And constitutive versus induced. And so constitutive and is really basically saying it's on all the time. Okay. So this is typically you'll see this when we talk about genetic engineering. GMO. Okay. And so constitutive promoter, for instance, is on all the time. And I'll put that in quotes, okay, because it's not necessarily on all the time the same. But again, constitutive has a tendency then to look like it's growth associated, okay, for example. Induced is one where the classic lac operon system, where you have the time course of where you're growing something, and the fact of the matter is you can decide when you induce it. You could throw the inducer in here, like if we're using the lac operon, it would be IPTG. I could throw it in early. I could throw it in at the end, okay? And so an induced one, okay, could look associated if you do it early, or it could look like it's growth dissociated, IPTG, if it is done late in the actual culture. And so the product doesn't actually start to form until you add it, okay? And you can get very different results then. So here you would see it would look like that. And this one here, if you don't induce it, then it won't make any at all until after it does it, and then it'll start to accumulate it later. So that's it. Those are, again, lots of different terminologies and so forth. But you can see that once you get these time courses, you then have to digitize the data. And then from that data, then take, if you will, numerical derivatives. You can fit the data. For instance, if I have a data set and I want to, get that, I can take differences like this, okay? Or I could fit it to a curve, okay? And once I fit it to a curve, I could then maybe get better derivatives, if you are, for slopes and so forth, okay? And ultimately, the last thing I should have probably mentioned here is if it's a continuous system, then productivities are really easy because it's what comes out of the reactor. Okay? You simply look at it, you see what's flowing out of the reactor, and that is your product that's being made. That's it. Okay. The recorded lecture notes that I went over were pretty general, and I think one of the things you're going to have to understand is until you actually crunch some numbers with one of these, it will be pretty abstract. In the case of something like a simple time course, it's pretty straightforward, but I wanted to have an example here where it's pretty complicated. The paper here is about, it's about Botricoccus, which is the hydrocarbon-producing algae. And what they do here is they actually take the cells and they add a hydrocarbon layer to the top. It's an octane layer. And what that does is it extracts the oil and then they can recover the oil, and then they can replenish the media, and then do this repeatedly. So what it represents is sort of a repeated integrated extraction type experiment. So that's the basis of it. The interesting thing about this is that it's because of the nature of it being an extracellular product that's partially extracted repeatedly. It's quite complicated to try to analyze it, and they don't really, in this particular paper, do much analysis with it. They certainly give the impression that this is successful, meaning that this is a good idea to repeatedly use the biomass, and certainly conceptually the fact that you could use the biomass over and over again. But in this analysis that I'll be doing is when we actually look at the data, you may come to an entirely different conclusion about that. And it appears, as we'll be showing, that the productivity is actually declining, meaning if they had just simply started over again with a fresh inoculation and the same time frames, using the same reactor volumes, they would have made more hydrocarbon than if they had done this repeated extraction. I'm just going to go down through, and show this. So a lot of numbers and so forth have to be taken from the methods, or in some cases even, it's not cooperating very well here, or in some cases even assumed. This little figure that you see in front of you here shows it's in a reactor system, and what they're doing is they're putting this solvent here as the octane. And then they grow the algae, the Botricoccus, in the presence of that. And the hydrocarbon is extracted into the solvent phase. And then they'll remove the solvent, let the cells settle, and put in fresh media. And then they'll continue around this cycle 3 times. And so that's the basis of the actual experimentation itself. The figure that in particular I think really summarizes the crux of this particular paper is the figure 6 here. And what happens is that they're looking at basically an optical density measurement. And so this is the growth of the cells. And then at the end of a growth period, which varies somewhat in time, in this case, they're going through 24 days and then on out. It's a pretty long culture. They then do the extraction. The weight declines for 2 reasons, as we'll be seeing. It declines in part because you're extracting the hydrocarbon out, so obviously there'll be less weight. And then secondly, I think it's just stress, because if you do the calculations, the amount of hydrocarbon taken out is not enough to account for this drop in density of cells. And then it grows again, then extracted again, and then grows again. And since this is a cumulative plot, of course it looks good, right? The concentration of cells keeps going up, and the concentration of hydrocarbon is also going up. But of course, anytime you have a cumulative plot, it will look like it's accumulating. That's the nature of it. What's important is the difference. And you can see here that you have the initial extraction. Then you have this is being added. So this is how much more there is. And then this is again how much more. You can kind of see that in this third time of extraction, clearly it's smaller than it was in the second period of extraction. So that's some hint that things are declining with time. Even though there are more cells in there, the amount of hydrocarbon that is being recovered is actually declining. Now there's several aspects of trying to think about this problem. And one of them is that remember that the extraction is not complete. In fact, they state in here that it's roughly 50%. And so what that means is that this initial extraction that you see here only recovered half of it. So half of it is still there to be extracted the second time. Therefore, the amount that's produced the second interval is a combination of what is new that's been produced during that time, plus what is being extracted that was not extracted in the first time. And that's true now for the third time of what was not extracted the second time, and what's left that's extracted from what was not extracted during the 2 extractions from the first time. And so that's a series of things that I'll be going through in the actual calculations, is to take this and take the digitized data. It's not so much a time course, like here's the time course, a classic thing where you can calculate productivities, at least of cell biomass here. But there's only hydrocarbon analyzed at 3 different time points. And so from those numbers then, a lot of this is really a mass balance problem. And as I'll be showing you then in the next figure here, table 1 gives some additional information, actual numbers on cell growth and biomass here, as well as hydrocarbon extraction content. And these are really critical then for ultimately then really figuring out how much cells are present, how much hydrocarbon was removed, and then using the information of the time frames, which it turns out are slightly different. The intervals are different between each one, to end up calculating the productivities. Now to do that, I have a spreadsheet here. This is actually a homework problem for ChE 438 a couple years ago. And I will be assigning you individually some different ones other than this one. So many of those are going to be much simpler than this, but this is a good example then to make sure you can kind of understand. So what you'll see is I snippet the actual figure into here just to use this as a basis. Provided a link to that, and then this is the kind of thing that I really want you to understand by looking at this is the kind of documentation that I want you to have in that homework. This includes a narrative, like you'll see in this here. And if you look down here, you'll see then that there's actually, you can't see the bottom of this, but if I move this up just a tad, you'll see the bottom. So this is the executive summary. And having a brief executive summary of what my conclusions were. And what I'll be showing you is that the actual productivity is actually declining. And the new hydrocarbon is, when you account for that, what you see is that actually the volumetric productivity in this case is actually declining with time, with these successive intervals. So the cells are actually producing less hydrocarbon, even though there are more and more cells there. It appears that the cells, once they're extracted, do not continue to produce material, and they're just basically blocking light and wasting space in the reactor at that time. That is definitely not the conclusion of the paper, but the intention here, of course, is for you to know that if you're going to analyze data critically, you can't simply take the conclusions that you see for granted. One of the things about analyzing data is that you need to come up with a clear hypothesis of what you think is going on, because then that becomes the basis of what numbers you take and how you go about the calculations themselves. Okay, so it says here, it would appear that the next rounds, you basically have successive intervals of growth and successive hydrocarbons, where it looks to me like clearly you can see that it's declining in growth up here. And ultimately, what you'll see is even the productivity is declining once you take into effect the incomplete successive hydrocarbon extraction. If we look on down then at this, I want again to emphasize that even looking back now at this spreadsheet, which I had made a couple of years ago and made a lot of annotations and a lot of notes and so forth all over it, I still have found that it's not nearly as complete as I would like it to be. In large part because the basic idea of, for instance, showing units is that units themselves really don't give meaning. Okay, grams dry weight could be total grams dry weight, it could be the change in grams dry weight, it could be the change of dry weight in a given interval, and the liter could be the liter of media, it could be the liter of media plus the solvent. One aspect that's interesting in this particular paper is that the extraction phase, which you see right in this comment right here, they give the concentration in the extraction phase. But since they add an extraction phase that's half the volume of the culture, immediately the numbers look better because it's concentrated into that phase. That's a good thing from a standpoint of processing, because you'd love to add as small a volume as possible, but you have to then recognize that the units are just simply grams per liter. And so if there was 1 liter of media and then half a liter of solvent, if you had 100% extraction, you would immediately double the concentration. So you have to be very careful. I mean, the liter here that you see in this unit could be liters of solvent. It could be liters of media plus solvent or liters of media. Any one of those. In fact, you can even express it per volume of cells, for that matter, be the concentration inside cells. And so keep that in mind. Now, other useful information for this is that since they give the biomass at each interval, the harvest interval, it allows you to do kind of a successive mass balance, and you can actually find out how much they grow in each of the actual intervals. And that's intended to be shown here, where I'm trying to be very clear about breaking this down into essentially 3 batch intervals. There's a batch here where it grows, and then the cells happen to be thrown back in. And then period 2, there's an additional growth that now this is the new cells plus the cells that were left behind. And then the third one here, this is the additional period 3 of growth. And yet, I mean, obviously there's way more cells in there than grows in that third period. So it's actually dominated by older cells that were already previously extracted. If you go on down here and look at some of the units and so forth here, I note that this is not a cellular productivity, but it's recovered hydrocarbon, because not all of it is actually extracted. And so even though it may be expressed as a grams of hydrocarbon produced per liter per time, as you see over here, it's actually the extracted. And since the extraction efficiency is pretty low here, since we're trying to maintain viability, keep the cells alive, they note that it's roughly about 50%. So only half of it is being extracted, and the rest of the productivity remains inside the cells. And in this particular case, since you extract it again later, that material that was made before that you didn't extract is available to be extracted. So it kind of makes it look like there's more being made later in culture, when in reality it's just being cumulatively extracted. There's some other calculational things in here. I mean, one of the questions that immediately came to mind to me was, if you take a look at this, here you have growth of cells, you extract them, and then your next data point is lower. And to simply ask the question of whether or not these cells here, minus the hydrocarbons, equaled the cells that were here, or if there was a loss in weight that might have represented killing cells and things like that. So that's what this particular calculation is here with the blue line here. And what I note is the mass loss is greater than the hydrocarbon that's actually extracted. So that means there's other cell disruption, death happening in there. That is worth noting because, of course, one of the conclusions of this work, this analysis, is that they're unhappy. And so even though there are more cells in there, they're not making more product. As you go down further here, this analysis in this section of the analysis here is a way of basically taking into account the fact that for the first extraction, you have a certain amount of the material that is left behind. And if you had 50% extraction, what that means is that if I extracted 50% with one extraction here, then half of that should be extracted again the next time. And then by knowing the total amount that had been extracted in that second interval, then what you really know is that this material right here is what was made, if you will, by the new cells that are there. And so again, so that if you look at this from the third extraction, you'll notice this number is half of that number. So each extraction gets a contribution from the previously period, and you have that period there. This is actually half of that one. And then this represents the, if you will, new material that was extracted during that particular interval. And now, again, since they never really do a hydrocarbon analysis where they completely extract the cells, they do make a comment in there that there was about 50% extraction, and that's an assumption that you actually have to make these calculations. So it's really important that when you carry out this kind of an analysis is to recognize what data you have to do the calculations, and sometimes it's not going to be given, or it'll only be able to estimate it. And so you have to make sure those approximations are very clearly annotated. This graph here is an interesting way of now looking at the analysis in very different ways. What you can see here is this particular one is looking at the amount over each interval. And so if you take a look at the blue line here, which you could tell, of course, if you have a spreadsheet, you can see that that's coming from here. And each one of those is just looking at how much was recovered each time. So this is kind of like the money in the bank, if you will, recognizing that you didn't manage to extract it all out of the culture. And this is the basis, if you will, of the conclusion that it's improving with time. That is that each interval shows a increase in the grams of hydrocarbon extracted per culture per hour. However, remember that the material that's coming from these extractions here includes that which wasn't extracted the first time if you had just simply killed them and extracted all of the material and started over again. Another way of looking at it would be then to look at it just in terms of what was new. So on this diagonal over here, you can remember that this was what was made in the first period, second period, and third period, subtracting away what was actually extracted. And that's what you'll see if you see here that these are referring to. And in that case now, that represents the orange here, and you can actually see that the amount produced per gram of new tissue, that is that this is the grams of hydrocarbon produced for the new cells that grew during that time period was going up. But of course, again, this is somewhat artificial because they're getting credit, if you will, for the work that was done by the cells before that were actually being extracted. The point of this is that one can see very quickly that depending on how you calculate productivity and the details of that, you can certainly make a very strong case for, in this case, integrated repeated extraction being beneficial because it looks like things are actually getting better and better. But remember that in order to do this, we had to be gentle with the cells, and that's why the extraction efficiency is so crappy. That's actually the most evident if we go to the grams of hydrocarbon produced in the interval itself. And that's the final one here. And so the amount that's produced within that interval is reflected then by, again, these numbers on the diagonal. And what you see here is that it's actually saying that the amount produced is declining with each interval. And so each interval, it's actually sort of getting worse. The intermediate one here is just an average one, just using the time from time zero, if you will, of from here to here, then from here to there, and here to here. So it's like an average over the whole time frame. And again, you have to be careful about interpreting those types of things because of the fact that you're getting benefit later for these things, for the material that was actually produced earlier but just simply wasn't extracted. And so from a biological standpoint, what I'm saying here is that this basic idea that repeated extraction is more productive is ironically less productive, meaning that if you just simply started it over again, even at a low cell density, and started over 3 times, you had actually made more material than if you had done this repeated extraction approach. There's some other things that this probably represents that's important to recognize, which is more like a physiological interpretation. What it means is the cells that are left behind after they've been extracted don't seem to be contributing. So to me, this is suggesting that the cells are making the hydrocarbon only once. And as you know, and leaving them in the reactor, they don't have like a regulatory mechanism to recognize that they made the hydrocarbon, and so they're not going to replace it. And if they're not going to replace it, it makes no sense to leave them in the reactor at all. And if you think about it, it kind of makes sense because this particular algae, the hydrocarbons are on the outside. And if they're on the outside, then why would there be any feedback regulation into the metabolic pathways? And so you can see that sort of my interpretation is probably nearly completely 180 from what you actually see in here. This idea that this technique would be applicable to exploit continuous extraction is, quite frankly, a dumb idea. Okay, it doesn't, well, I mean, not a dumb idea, it's a good idea, but the data doesn't support that this would be a logical way to do it. It's actually suggesting to me that you should be killing the algae as they produce it and move on and go back to happy oil producing new cells rather than blocking the light or whatever else is declining in the culture in the later phases of culture. So that's it. That gives you an idea. This will be posted actually on a website, botricakis.org. And what we'll be doing is giving a series of additional papers that we would like to do some of this type of analysis where you will have to digitize the data, get numbers from it, and then from that actually do some calculations to get used to this idea of calculating productivities on a volumetric basis, on a specific basis, as well as doing calculations of yield as well. And